Okay, so I'm starting. So this is a talk, a new era for graph queries, ISO IEC 39075 GQL. My name is Stefan Plantikow. I'm Principal Software Engineer at Microsoft, and I'm here today in my role as the ISO editor of the GQL standard that this talk is about. So I have quite a few packed topics. Essentially, I want to, at the end of the talk, that everybody has an idea of what GQL is and what you can do with it. So we're going to talk about GQL, core concepts, its graph model and catalog, queries and pattern matching, various related topics, updates, query composition, and so forth. So what is GQL? You might have heard about it this year in April. It came out. It's an ISO standard. It's the correct term.
Sorry for interrupting, but you're sharing only the preview of your slides and not the actual slides.
That's what I was trying to test. Okay, let me stop then. Then I have to do a full share of the screen, I think. I try to share the window.
Yeah.
Okay.
Yeah.
Okay, let's do it like that then. Okay,
yes.
Is that better?
Here we go.
Okay.
Yeah.
Okay.
Perfect. Thank you.
Good. Okay, so here we are. So the correct term is actually information technology, database languages, GQL, and then it has this long complicated number because that's how ISO standards are referred to. It is a new graph database language standard by the so-called SQL committee, which is no small feat. It is the first time in the history of database languages that the same committee that has done SQL for 30, 40 years has done a new database language standard underpinning the importance of graphs, especially now in the age of AI, as the primary model for storing data. Originally, we did GQL was motivated by the growing adoption of property graphs. We all know, and I'm sure you will see in these slides and many other talks here at Node today, is still the fastest growing database segment by far. And also the observation that we were beginning to see fragmentation across vendors. And so that is usually a good point in time to go for standardization. So I'll talk about the history of it in a moment. And it's fairly large. It's 630 pages. It's not essentially a light read. So a little bit the history of all this, in sometime around 2010, we see first articles on property graphs. Then 2011, Cypher was released, right? We got Open Cypher in 2015, and that's where the kind of fragmentation began to appear around that time. Other vendors created their own languages, PGQL, GSQL, research languages like GCore, and that led to the publication of the so-called GQL Manifesto in 2019. And that was basically an online poll and document asking the database language to pull together and do a standard before this kind of fragmentation continues. And that got us started on the ISO project. Now, writing an ISO standard is a tricky affair. I will not have time today to talk about those details. That's a different talk. Nevertheless, in 2020, we had the first draft, and then it took another 4 years to actually get the document to the state in which it is today, which is an international standard for the graph database industry. Before we move into the actual technical content, might be good, though, to reflect a little bit. Why do people actually do standards? And actually earlier when I did this slide today, I just Googled for this. So this is like a stock answer from ISO or one of the other standardization organizations. And I've added here the bits in pink, essentially just. So why do you do standards? To ensure consistency of essential features. For example, it's really good in a field if people agree how graph pattern matching works, because then they can talk with each other. If you see a slide at a conference and somebody puts a graph pattern on it, you know what it means, right? It is a device to codify the latest technology and facilitate its transfer, right? Here, it's more about the state of the art, how to query graphs so that vendors do that in the same way, right? Standards help ensure safety and quality. That is maybe will not be immediately that visible today for my talk, but there's a lot of security considerations in the GQL standard. And then prevent or overcome problems caused by lack of standardization. And here I already mentioned the beginning market fragmentation that happened at the time when Open Cypher came out, with multiple languages being around that were very similar to each other. What were our goals initially when we started the GQL effort? Well, we wanted it to be an industry effort that addresses real-world needs, informed by research and community. We wanted it to be a universal graph database language that empowers users to access graphs reliably, enabling skills reuse, vendor interoperability, and data longevity. We wanted to further establish property graphs as the data model for storing connected data, and by doing so, growing the whole space and raising the level of abstraction also, so that graphs become an object that gets manipulated in the database. We wanted a language for all, for graph experts, SQL users, data analysts, programmers, right? Everybody. We want the language to be backwards compatible, and that, of course, is never an easy thing to do, right? One of the real feats that GQL has achieved is, I think, bridge all these existing languages, in particular Cypher, but also honor a lot of things that come from SQL in order to blend that into a new standard, right? And then last not least, of course, align with modern technology, Unicode and things like that. So core concepts. So this is maybe a little bit the dry part of it all. So what's the 10-mile high view of GQL? GQL is a complete database language. It's not just a query language, right? So usually, in the database language field, you use these terms DQL for queries. DML is the part of the language that has to do with data updates, and DDL is the part of the language that has to do with schema changes and, creating graphs and things like that. So, and GQL covers the whole gamut of all that. So we have an abstract system model. I get to that in a moment. There is, of course, the property graph model and how they're stored in a global catalog, conceptually stored. There is the whole interaction flow, how the user interacts with the system. There's graph pattern matching. I'm trying to spend a great deal on that later. There is a schema model. How do you describe the structure of graphs? Security considerations, syntax considerations, and so forth and so forth. And last not least, toward the end of the talk, I also want to talk a bit what it actually means for a vendor to correctly implement GQL. Okay, let's get into it. And just briefly this here. So what is kind of the abstract system model? When you write a standard, you have to somehow make assumptions about how the world looks like in which you navigate, and ideally you do that in a way that is abstract enough to allow many different kinds of implementations to exist. And so that in GQL is called the environment. On the left, we have our user. That is an actual user, like, a person. And they want to do something. And they do that with an application program that we like to call the GQL agent. And then the GQL agent uses a component of the implementation. That is the thing that you buy from the database vendor that is called the client. And for example, in Neo4j, that could be the driver suite, right? And then the client talks to a server. And then the server has two components. It has a conceptual place where all the data is stored, that's GQL data. And then it has a conceptual place that is basically a registry of all the data that is stored, and that's called the catalog. We'll talk about that later. So then to make that a bit more, understandable and not so much stay in the abstract here for the talk, I've picked an example query, and we'll go through that example query as we go through the various topics I want to talk about today. So what's the example query? A taste of GQL, query and update graph data. It's a fairly simple scenario. You see it starts there with a thing called session set country equals GER for Germany, where we set some session parameter. Then we start a transaction, right? And then we actually get into the actual query. In line 1, we somehow choose a graph to query. Then we do some pattern matching. We do some filtering. After the filtering, we actually decide that we want to materialize edges based on what we found and insert new edges into the graph, and then return an aggregate that records how many edges were added. After the end of the main part, essentially, we commit the transaction and close the session, right? And this is maybe not the most complex query you could do with a graph database, but it will serve us well here to talk about all the different facets of GQL today. Okay, sessions. What are sessions? GQL features a stateful session model, and stateful because it tracks a lot of stuff. It tracks basically the context in the catalog called the schema. We'll get to that in a moment. The graph that you're going to work with by default, the time zone, eventual parameters, and so forth and so forth. So that's the umbrella in which everything happens. And then in the session, requests are processed sequentially, and that's really where the real meat is. Then the other bit I want to talk about briefly is that, like SQL, GQL defines a transaction model. It provides syntax for explicit transaction demarcation, like the one you have in SQL. You can say start transaction, rollback, and commit in syntax. And there's also the concept of access mode, so you could have perhaps read-only transactions, right? So in general, then when you talk about transactions, people often ask about, yeah, but what about isolation levels? Isolation levels is a really tough subject, which is why we don't standardize them, right? The standard assumes serializable transactions, but of course knows that real-world products often will do something slightly different. Okay, so we kind of have the scaffolding in place, right? We had a session, we have started a transaction, now we're actually going to run our GQL query. And so now let's talk about graph model and catalog. So here we are already in line 1 now of the example query, and there it innocently says use social graph, right? And that sounds fair enough. We're going to query some kind of graph, but where does that thing actually come from and how does it look like? Well, already mentioned, GQL has a notion of a global catalog. You can think of it very similarly designed to a file system, in particular Unix file system, as a hierarchy of directories, right? You start at the root and then it goes down, down, down. The leaf directories are called schemas. And then schemas are where the actual data objects live. And of course, most prominently, these are graphs, but GQL recognizes that there could be other objects in the catalog, such as tables or user-defined procedures or any other future extensions or possible vendor extensions, right? So this gives essentially a unified view for providing multiple data assets, through a naming scheme and making them all accessible to queries. So then, of course, property graphs, right? If you do a graph query language, you have to say what your graph looks like. GQL firmly is focused on supporting property graphs consisting of nodes and edges with a syntactic identity, with arbitrary many labels or no labels. So this is the difference, right? Sometimes products don't support that in GQL. For example, edges also or relationships also can have no labels or multiple labels. And edges can also be undirected. So the property graph model in GQL is a bit more generic, but it's also quite possible for implementations to not support that full generality in the implementations. So we have a fairly flexible property graph model definition. So then, of course, the meat in a property graph are the actual properties. And there, I think a lot of work has happened in GQL to kind of define a type system for properties that really covers a lot of the needs and strikes a good balance between kind of modern expectations and also SQL compatibility. So there are booleans, Unicode character strings, there's a dedicated type for byte strings, there are various numeric types, integers, decimals, floating points, even with support for proper IEEE 754 floats, which is something that SQL does not have. For example, there are temporal types aligned with ISO 8601, which is the de facto standard for doing temporal data, lists, records, and so forth, right? So again, here you see that GQL does not force vendors to support all of those. It just defines those data types, but minimally required are, of course, Boolean, integers, floats, and strings, because that is the common baseline among all the languages that we used as the starting point for defining GQL. So queries and patterns. Let's talk about that. So here we are in the second line of the example query. Right now we're doing pattern matching. And if you know Cypher, that should all look very familiar, and that is intentional. I think the syntax for pattern matching as Cypher served as the starting point for defining pattern matching in GQL. So if you've never heard about graph pattern matching, though, I think it is one of the most important innovations in the whole field of query language. It's a very intuitive ASCII art syntax for describing basically what you're going to get out of your graph. It has been called by a very famous person on the SQL committee, whose name shall not be quoted, the best syntax for describing joins ever invented. And the nice thing about pattern matching is that it does not only apply to getting data out of the graph, but also in other places. It has been used for updates. It's used in GQL for updates. It's used for data schema. It's used, for example, in Neo4j for constraints. And it's universally adopted. So pattern matching gets an update in GQL. And so the first thing that has changed here is that the way you can select nodes with labels has become substantially more powerful. You can essentially express arbitrary Boolean formulas over labels to say which nodes and edges you're interested in. You can, of course, filter nodes and edges by properties. You can filter them with predicates, even written inline in the pattern. And of course, there's now also new syntax for the undirected edges supported by GQL. So that's a substantial upgrade. Then we have, of course, simple parse patterns. And, the simplest way to take the elementary patterns we have seen here on this slide is, of course, to put them together, like you might know from Cypher, person knows person, or perhaps if you want to use undirected edges, you could write person knows person, undirected edge related to person, right? But usually what people want to do is, of course, like with children, you do it once, you do it twice, you do it forever, right? They want to find arbitrary long chains or very long chains of those relationships. And so that's variable length patterns. And here we see a bit of a change in syntax. Over Cypher, you see here, for example, in variable lengths that the quantification moves to the right of the arrow. So that's a bit of a difference. So you write n, m for saying I want between 3 or 4 nose edges, and then the clean star or the plus for arbitrary many or 1 or more. A new thing in GQL are the so-called question patterns. They are kind of like variable lengths. So it's kind of like saying, I want this at most once, but it's okay if it's not there. And the difference to a regular variable length pattern is if it's not there, you get a null binding, essentially, right? So that is also a new feature in GQL. So then, of course, once you have, all these beautiful long chains of patterns, you want to start searching parse. Of course, the classic one is the all, but there are other ways you could search for parse. You could be interested in any shortest, in all shortest. You could want top K shortest. GQL even defines shortest K groups. Groups here refers to the fact that if you search for shortest path, you could find multiple paths of the same length, right? And if you say, give me the shortest 3 groups, then you get basically all the shortest paths, all the second shortest paths, and all the third shortest paths together, right? So that is also an addition coming from GQL. And so next up is complex patterns. So in GQL, we have new choice operators. So that is really something very useful. It allows you to basically say, well, I either want to find a path that looks like this, or I want to find a path that looks a bit different. And to some extent, you can do this today, right? You can write, for example, on an edge pattern, you could write likes or loves with labels. But the nice thing about these choice operators that it also works with longer paths, right? So you could say I either want to find people that like each other, or I want to find a path where, I don't know, 2 people love the same person in the middle, right? And the real power of these new operators really begins to shine when we look at nested quantification. This is perhaps the biggest advancement to patterns that came out of the GQL effort, and that essentially allows you to do variable lengths, but where regular variable lengths only works across edges that have kind of the same labels or relationship types, nested quantifications works with these more complex path expressions, right? If you see here in the middle of the slide, the example, the dramatic love triangle, where we basically search for long chains of pairs of people, that love the same person, right? And things are kind of quantified over that, and then you can have arbitrary long chains of those kind of patterns, right? And there's a lot of interesting use cases around that, and that adds a lot of flexibility to pattern matching. I mentioned in passing another topic that the committee had to deal with as part of the standardization effort is the topic of match modes. There are two fundamental ways in which you can do pattern matching. One is the Cypher-like mode called different edges, and then there's the other that you could call the SQL join-like mode that is called repeatable elements, and GQL supports them both. Moving on a bit, I said earlier already that graph patterns in general are a super useful tool, not only for describing the data you want out of the graph, but also in other contexts. And another context is the topic of graph schema. It's outside of the scope here of in half our talk today to get into that in depth, but GQL defines a whole essentially concept of how you can describe the structure of the graph in terms of the allowed nodes and edges. And it reuses pattern-like syntax to do so. I'm just showing here a single example here on the slide where you have an employee node, and it can have it always has to have an ID property that is an integer, but in that particular graph you can also have person and employee nodes that have additional fields, and dog and employee nodes, think of a police dog maybe, that have different additional fields. And then you can say, okay, in this graph, it's all about which persons over supervise which dogs, right? And so you see here really in using the same or very similar notation that is very familiar already. If you know a little bit about pattern matching, we can use to describe the structure of the graph. And the reason that was very important for GQL was that the vendors of the table really represented a very different spectrum of implementations, and that and that had to be supported by the standard. And of course, if you are a vendor who's interested in implementing static typing, then of course you need to have a schema so that you can perform static typing at compile time of queries. And for that alone, a graph schema is needed. But of course, it is a very useful device in its own right. Okay, so we moved kind of past the pattern matching stage. Now we want to do some post-processing with filter. And so basically, just as you might know from Cypher, GQL supports a lot of the relational operations. It's done a little bit differently. GQL does not have Cypher's with. It splits it up into things like let, filter, order by offset. But you get to do all the things you're used to being able to do with the driving table after pattern matching. Updates and aggregation. I mentioned GQL is a language that has a full update language. And here, I think the biggest change is, well, it doesn't have merge yet. Okay, that's maybe a deficiency. But then part of and parcel of aligning with CQL that created for inserting nodes was changed to insert. So you insert into the graph with insert. Here, insert one node, insert two nodes and an edge, create an edge between, two nodes, very similar to Cypher. Setting and removing also works very similarly. If you're familiar with Cypher, you get a full update language for basically changing properties, deleting nodes, deleting edges. In the interest of time, I'll skip a bit over grammar. Over aggregation, I'll just mention in passing there are some slight differences related to aggregation. In particular, in GQL, there is explicit group by. Okay, query composition. I want to spend at least a little bit on that before we wrap it up. Composition is the root of language explicit. Oops, I think I skipped a slide. Oh, I lost one. Okay. Doesn't matter. Composition is the root of language expressivity. So GQL has a lot of ways of how you can build bigger queries from simpler queries. We have procedure calls. We have nested subqueries as an extension over what you had before in Cypher and similar languages. We have a full gamut of set operations. So there's a little bit more richness here in that department. One thing, though, I want to point out is that if you look at Cypher queries, they basically form a tree. And GQL queries actually form a DAG. Here we have a slightly larger query that essentially shows that. and I'll use that as my last example, maybe for a large query here. We come in here and we find mail nodes, and then we get the addresses of those mails, and then you see this next here. Think of it a bit like a Vistar, but it's a Vistar that's kind of supercharged, because in the next step, it goes into a union, right? And the interesting thing is, when you pipe a binding table into a union, what should happen, right? And what GQL does here is basically it feeds the outputs that come here into both arms of the union, and that way essentially you have created a DAG structure in your query plan, and so here the query is a bit more powerful. Okay, so maybe last quick topic here: conformance. When you write an international standard, of course, the question is, what does it mean to support GQL? Basically, there are two ways you can think about that. You can take a piece of GQL and ask, is it actually GQL? Usually more important is when you go and buy a database product, does it actually support GQL, right? And we want to help vendors to adopt and tailor the standard to their needs. So that doesn't mean that everybody has to do everything that's written down in the standard, right? And so conformance can differ on key points between products. There's flexibility on which graph schema model variant is supported, the set of data types that is supported, the Unicode version that is supported, the optional features that are supported, yada, 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 right? The important thing that a standard kind of wants from implementers is that if you provide something and say, okay, we support this feature that is defined in GQL, then a product should behave also like how the standard says that feature should work, right? And so a way to think about GQL is provides a toolbox. A lot of its features are optional. This is intentional to foster adoption, to support different kinds of implementations, such as read-only implementations, and to allow and encourage controlled innovation by vendors. Tiny look into the future as you're getting to the end here. What's next for GQL? I think now that the standard is out, it's for vendors to implement, and then innovate on top. For users, of course, is to adopt and demand vendors to support GQL, to have portability, to kind of secure investments into graphs for the long run, right? And then that's kind of more on the external side. And I think in standards, there are so many topics that you want to pick up. Cheapest path is being worked on. Vector types for AI is being worked on. And there's a lot of interesting ideas on the horizon, from graph projection to information schema graphs to temporal graphs. I'll leave it here. I'm a bit short on time. GQL 39075 2024 is here. I think it's a really big milestone, cementing the achievement that the property graph world has reached through its hard work over the last 15 years. It's an exciting time to be in graphs and AI. And of course, if you're in this talk, I hope you're going to use GQL in some capacity. And I'm curious to see what graph you will build and query with it. So I'll stop here.